The talk of today is about the new features in MPI+. Here is the history of the MPI standards, and you see here is MPI+, and here already the upcoming MPI+1, which is scheduled for end of next year. And in principle, I have here about 19 topics about MPI+, and about another 5 topics about what is scheduled for next year, MPI+1. And this means I have only between 1 and 2 minutes per topic, but I have many slides with background information. This means I want to be really fast and going only through the main things. My co-author is Tobias Haas, and he has, for example, looked at the partitions and has provided the example there, and we will look at that later. And all these slides are based on, in principle, my complete MPI course at the HLRS, which is a 5-day course on whole MPI from MPI+1 until MPI+4. And therefore, the acknowledgements also apply to this course. First topic is large counts. With MPI+3, they added additional routines that you can examine how long is a message and so on, which goes beyond the 2 billion of an integer, because the counts in MPI are all integer. And now with MPI+4, we really define for each MPI routine that has an integer count an additional large routine with an MPI count argument. And it looks like that. That you will see here between the original MPI receive in C and the modern Fortran version, you see for both, you see the large count version where the count arguments are. They are now MPI count, this means 8-byte integers. And in C, it is with an additional subroutine name _C, and in Fortran, it's directly overloaded with the same name. And with the old Fortran interface, nothing was done. It's already background information in principle on the way of being outdated and going away. Here examples in the background how such interfaces now look like. Next topic, persistent collectives. There was an idea, let's do persistent collectives. In MPI+3 or MPI+1 already, we had these persistent point-to-point routines, communication routines. And the idea behind persistent routines is when you have a time step loop, for example, and inside of the time step loop all the time the same communication pattern, that the MPI library then can optimize your communication pattern, use initialize all the communication, and then in each time step you are calling start all, and the MPI library has a chance to optimize. And of course, also collectives may be additionally optimized on the given hardware network, and that's the idea behind. And the problem was when we tried to do this, that the whole wording in MPI about what is a non-block routine and so on, all this wording was not really written in a precise way. Therefore, the idea was really to write it now in a perfect way. And as a result of that, we really changed the definition of non-blocking. In the past, non-blocking meant only incomplete, and now we changed it to non-blocking is now incomplete, and it must be a local routine, because the reason is very simple. These init routines of the persistent collectives, they will be incomplete, but they will be not local, because for the optimizations they need to communicate. They are still collective, and to name a routine non-blocking that is not local, that blocks, that would be, you can do such definitions, but it makes no fun for the users. And the result of that was that we have a complete new naming. We have so-called stages in MPI: initialization, starting, completing, freeing, and then the operations can be different things, and procedures can be in principle first local or non-local, and then procedures can be completing procedure, procedure can be incomplete, and so on, all these things. And non-blocking now incomplete and local, and blocking is the contrary. This means completing or non-blocking. And examples and so on. And therefore, for our normal non-blocking procedures, they are still non-blocking procedures. No, this means for the normal world, no changes in principle. And the stages, initialization and starting up together, the initiation, that's the I routine, and then we have completion and freeing, the test or wait routines. Okay, and the nice thing now is the broadcast init. They are added, and they are collective operations, and for collective operations, and they are blocking and collective calls. But of course, incomplete, only initializing the stuff. Okay. And next topic, partitioned point-to-point communication. I don't like the word, but the interface is very interesting. When you have MPI plus OpenMP, how do you program it? Maybe for the many threads, or maybe MPI plus GPUs, and you want to send one big message, and then you send parts of the message. Each thread can send a part of the message by calling this p-ready. And this means you can split your messages into these partitions. And the same on the sender side, on the receiver side, can do it different on sender and receiver side. And as background information from Tobias has these examples here. And I must say, the first thing he detected was that the examples in the MPI standard are full of bugs. And he tried to get it now in a perfect shape that there exists a real example. And okay, the rest you may do when you have interest through the discussion later. And then the new sessions model. Who of you is a library writer? Two, and here? Okay, library writers have in principle a small problem that the application can initialize MPI, but the library needs initialized MPIs, and who is doing it? And typically they write software like in my library init, I'm doing an MPI init if it is not yet initialized, and at the end I'm doing it in the same way, and so on. That's not really good style. And for that, we have this new sessions model. Each library can do its own init, and at the end, its own session finalize, and that's helpful. Okay, and we have also an additional interface for the sessions to get the argument set that was handed over when starting the MPI processes. This means the session model is a method to initialize MPI for independent application components or these software layers. And the next topic is new ways for hardware-based split of communicators. With MPI 3, we have this MPI split type to split our MPI convert or other communicators in shared memory islands. This was often used for optimizations because then you can do things in a very fast speed inside of an MPI, inside of a shared memory system, and other communication in between. And in principle, the problem is when you want to have it, for example, not on CC-NUMA nodes, you have it only on NUMA domains, on sockets, your island, then you were lost with MPI 3. All vendors have done some private methods to solve the problem. You can say, okay, I want to have it on for NUMA domain. And now we added 2 additional features to the MPI standard, type hardware guided and type hardware unguided. With guided, you can say, I want NUMA, and you get it. The problem was we had not the time to standardize the terms like NUMA that you can really write ported software. That is ideal that it will come in MPI 4.1. Okay? And the other thing is unguided. Unguided splits down to the next level. But exactly for that, I did a very bad example, an ugly example. Here you see I started on 5 CPUs, here two NUMA, CC-NUMA nodes, and 1 additional CPU, or here I'm using only 1 CPU. And therefore, the unguided would split here into the 2 CPUs, here into the 2 CPUs, and here it would split into the 4 cores. That would be not helpful. Therefore, with MPI 3, with MPI 4, it was still not a perfect thing what we added, but for 1, we will specify standardized keys for the guided, and then we can be happy.
So with standardized, you mean things like I want a splitting on the basis of NUMA domains.
Yes, and then we have a keyword NUMA, and the keyword NUMA stands in the MPI standard and is not OMP NUMA for OpenMPI implementations and MPitch NUMA for MPI-CH implementations and so on.
And if a vendor provides an implementation that does not, if I request NUMA split and it doesn't do that correctly, I can actually complain.
Yes,
because the
vendor must correct it. Yeah. And the next thing, thank you for this question. It's going somehow back to our vendors. We introduced in MPI 3 the MPI neighbor communication. And the problem with the MPI neighbor communication was that in all MPI libraries, it was wrong. The implementation did not work for cyclic all-to-all communication with only 1 or 2 processes in a ring. And the result is we added additional examples in the MPI standard and also how to implement it when you want to implement it. And nowadays, in principle, the MPI-CH and the OpenMPI has really fixed it. It may be that still vendor implementations are very slow to fix this bug. Then that slide, that was the bug that was seen. Okay. And other small new MPI4 features are, for example, the info handles. They substituted the routine to analyze an info handle. They produce the routine MPI get info, MPI info get string, which is using a more friendly way to handle strings, maybe in C. The pattern was already okay tonight. Yes, and in principle, they added also additional text on this principle of set info and get info, because in principle that was only true in MPI2, that the get info of a communicator or file or window handle will not return what you set. The get info returns what is really provided by your MPI library. It removes what you wanted to have when it's not provided, and it adds all the features that the MPI library provided and tells you the defaults that are used. And they added also additional routine MPI com with info, the non-blocking version to the MPI3 routine. Then, in total, with the info handle, we added that now info handles can also be used for assertions. That's completely different. In the past, info handles were only used that you ask for some functionality, and the MPI library had the right to know what you want to have. You could tell, I want disk striping on 5 stripe units. If your computer center has no disk striping, then it was ignored. And with assertions, it's completely in the other direction. You are doing an assertion that, for example, you will never use MPI any source or MPI any tag on a communicator handle. And then you store this info handle for this communicator, and then it's forbidden for you to use any source or any tag on this communicator. And with that information, the MPI library is able to do faster communication protocol, because any tag and any source have some drawbacks in the optimization of point-to-point communication. The error handlers were also revisited in principle on the way of adding these sessions, and also on the way for future fault tolerance, but here mainly for the sessions, because there are many MPI routines that have nothing to do with communicators. And because with the sessions, the MPI convert is substituted by now a sessions word communicator, and therefore they decided to do all the error handling with routines that have nothing to do with a communicator, to add this error behavior to MPI consult. This means, in principle, when you want to have that errors are returned, always, you must do after MPI init the change of the error handler for MPI convert and MPI consult. This is a real change in the MPI standard. And there is a new else abort predefined error handler only for related communicator, for the process related to a communicator, not for the whole MPI application. And there are many some other additional clarifications in the change log one can do. Then the MPI forum added non-blocking versions of the send-receive routines. It means when you are currently using send-receive for communicating in a Cartesian application to the left, to the right, to the left, we send-receive, sending to the left and receiving from the right, and then in the other direction, in total six 3 dimensions such send-receives. Then you can now substitute the 6 send-receives by 6 I send-receives, and you then wait all for all these 6 handles. Then the whole introduction to the non-blocking operations were rewritten. I asked Bill Kropp that he really rewrites it, and I'm very thankful that Bill has really done it, and because when you are looking at the intro of MPI 3 or MPI 1 to non-blocking operation, it was all the time wrong. And when you buy a book about MPI, in those books, you can see a copy of this wrong text. It was terrible that people have not really shown the real story, because the real story is in principle first about communication and communication, that you prevent deadlocks, and more important, to prevent serializations. And the last topic really, and this depends not on the quality of the MPI library. That's the first goal of non-blocking operations. And the additional goal is real overlap of communication or communications and computation, but that depends on the quality of the MPI library. With RMA, they added an additional alignment for the memory that you can do such an info key for a minimum alignment. That's only a small thing that was added. And for the lock and unlock synchronization, they added also that you can allocate the windows to allocate shares. This was in all MPI libraries available, but it was missing in the MPI standard. And request free. In principle, request free should be used only for persistent communication. At the end, at the beginning, you are doing the init. At the end, the inactive request handle, you free it with request free. To request to finish an active send or receive request with request free, and that's in principle stupid. And we have added wording to the MPI standard to really tell this. Okay, and the MPI cancel. The cancel of send request was really now deprecated. It's a very strange thing. It's also it has a really performance problems, and in principle, my personal comment is never do a design where you need an MPI cancel for your non-blocking request handles. You may fill up at the end your non-blocking request handle with an additional empty message with a signal at the end. The work is done instead of doing a cancel.
But if you cancel on one end, if you cancel a receive operation and your cancel succeeds, does the send on the other end then fail? So do I have to catch the error on the other end?
Well, I have never looked at that. You should cancel it only when you don't. No, when you don't, and when you cancel the receive, the correct answer is then, in principle, after you have called cancel, you still must do the wait but the weight is guaranteed to be a local function. And then after the weight, you can ask whether the cancel was successful or not successful. And if it was not successful, then there was no receive. And when the other side sends a message, then the MPI then clearly says, you can send messages, but the receiver is responsible to receive the message. When the receiver does not receive, then you have a broken application. But not a broken sender, the receiver is doing the back of the combination. Does that answer your question? Okay. Size of is now deprecated. It was a strange thing added to MPI+. I was already a little bit against that in MPI+, and now after many years, it's deprecated. And other small changes in the tools chapter, there are, you may look at them in the change log or the details. And we added 2 new chapters about semantic changes and warnings. This means we have now a real chapter where we can write changes that we did from one version of the MPI system to the next. In principle, there have been all the time changes by deprecating a function or by removing an interface. But now that's the new thing that we have also real changes of an existing interface, changing the existing interface. For example, the MPI com.do the MPI com.I no longer propagates the inputs from the input communicator. Or and there is, in principle, there are changes. These are real changes. In principle, the warnings are also real changes, but normally no MPI application should have a problem with that. Okay, and of course, another type of how the MPI form changes the MPI standard are also errata. If you have erratas in the MPI standard, then we say, okay, from the beginning, when we introduce this feature, we change it. For example, all names starting with MPI underscore are forbidden for application programmer. It was an errata that we changed it, that the MPI is not only uppercase MPI, it can be mixed cases, lowercase m, uppercase p, lowercase I, underscore is also forbidden. That things errata can change also things. Normally, we try to change things with errata only before the implementers have implemented. Okay, and now the last minutes of my talk, I'm still in the schedule, is about some future. There are several active working groups, and I've mentioned already that the hardware guide, for example, these additional standardized names should be standardized. I have slides in principle for 3 areas. The hybrid and accelerator group has several ideas they want to add. For example, they will add also additional features to these partitions interface. They want to add to that also an accelerator binding. There is several things for accelerators because nowadays MPI libraries are able to use accelerator memory directly as send and receive buffer, and also to direct the communicators to accelerators.
Yes. So then, for example, in a GPU, every single thread will call a p-ready when it is written as part of the message. Then when everyone has written that p-ready, then the message is sent.
Yes, that's the idea of the p-ready, that you define a whole message, and for each portion you can decide, okay, portion 300 is done by that GPU, and it calls GPU ready with portion 300, then it provides exactly this portion. So it has provided this portion. One area is Errata to the MPI shared memory interface. One area is there that the assertions for shared memory interface, for shared memory communicators are still part of the MPI standard. But when you read the assertions, you can see that they do not work with shared memory programming. With these loads and stores through portions of the combined window, and this must be fixed when members of the MPI forum have already checked normally all vendors, all real MPI libraries. They nowadays ignore the assertions on shared memory windows. Therefore, it does not hurt when you have, but the current rule is in principle users, when you have a shared memory interface, a shared memory communicator, do not use assertions in these RNA synchronizations because they are wrong defined, and on this other side we recommended to the implementers don't use them, and the implementers did it, and that's already enough. When one side is not doing it, then it was already helpful, but we have to specify them again, because assertions are about removing the latencies of the local memory fences, to have faster local memory fences than they are needed. And therefore, that's really in the direction of strong scaling an important feature. And the other thing is Win sync and any other process-to-process synchronization. It is specified in the MPI standard, but the example, in the example, these Win syncs are only for sending data. Or no, here X is a shared variable is written, and this is propagated to the other side through a synchronization here in the empty message, using send receive only for synchronization purposes. And then the Win syncs are needed. And of course, that's in principle the memory fence rule, the general hardware memory fence rule for storing data, reading data, writing, reading data. This means that's a right read rule for the use of memory fences. The memory fences are these Win syncs. Of course, the hardware is everywhere the same and independent from your programming model. The hardware has also such a read-write rule. That's the point. And the read-write rule is exactly that. When one process loads a shared variable B, and then is synchronized to the other side, I have loaded the data, you are now allowed to overwrite it. And that was exactly in this example, the second half of the loop, that you tell back, I I've used the data that you sent me. Now you can override it. And of course, for this, you also need these bin fences, these memory fences, WinSync and WinSync on both sides. And there's also the last thing, a write rule. Here also you need it. And this will be added, this will be corrected, the text will be corrected, and all this example in the MPI standard. Okay. Means these two things here, they were missing in the MPI standard, in the example, and also in the binding text will be fixed. Okay, and progress. It may be that we delay this topic to MPI 5, but we try already to have it in 4.1. I'm not sure whether we can get this. In principle, we want to better inform the readers of the MPI standard that MPI can be implemented in two completely different ways. One way is that MPI is doing progress only inside of the MPI calls. And the other way is that progress is done by, for example, an additional progress thread asynchronously. And one of the doubles of progress, for example, is bsend. If you are doing a bsend by definition stores your message in a local buffer on the sender side. And when you later on MPI receive, then the MPI receive has on the other side no counterpart of MPI call. Means this can be delayed. And if you have MPI libraries that do not do progress, that do progress only inside of MPI calls, it may be that there's an example. Go to the next slide. Exactly this. That here in principle we have three message exchanges, message exchange epochs plus numerics. The yellow is the numerics. Numerics is simulated here by a sleep of 20 seconds. And in total, instead of needing 60 seconds, here 130 seconds are needed. To be more exact, here I did some small additional delays. And when you are doing the same program, an MPI library that is doing progress through an asynchronous progress line, the same program, identical program needs only 75 seconds. Because then each epoch is really finished. Here, some of these epochs, communication epochs, are not finished. They wait until the other process has already finished its communication, that the next MPI call will be done. That's, in principle, the problem of not having asynchronous progress. And to tell this story, in principle, also to the users of the MPI standard. Because in principle, nowadays it's somehow a hidden secret of the MPI standard. And you have only small wording in the MPI standard at a few locations, and when you are looking at these background slides, you find these locations, and you are surprised to find the major story on that, for example, in the RMA chapter. Okay. And the last thing what I want to mention is the Cartesian topologies. We are not active with that. We were active with that with MPI 4. It ran never in the MPI standard. In MPI 4, it was not voted in. Too many people were abstained. It was not voted out. It was not voted in. so too many people abstain. And maybe we try to get it again in MPI 5. We need more time for that to convince people. And in principle, we have with Cartesian applications, we have in principle about 3 problems. The first thing is Bill Rob write a paper how it can really optimize the Cartesian topologies. But in principle, he detected that nearly no MPI library did any optimizations. I hope that with this paper from Bill Rob, this has changed at least for MPI stage, and that then it will be changed also for OpenMP. Another problem is that the existing interface with this dims create and card create does not really fit to what people need. The dims create has no idea of Errata, and the card create has no idea, and the dims create has also no idea that you may have not 1,000 times 1,000 times 1,000 elements in your mesh, that you have an unbalanced 3-dimensional data mesh. Okay, well, that was my last topic. And going to my summary, with MPI 4, we have several things for better service and several things for better performance. Better service, large counts, the sessions model, the error handling, and more consistent wording of the standard MPI standard, the revisited terms and semantics, this introduction for the non-blocking operations, and adding these chapters of semantic changes and so on. And for better performance, of course, the persistent collectives and this partitioned point-to-point communication. And we have these new ways of splitting the communicators into islands. Of course, when we have only a NUMA domain, then we have no first touch problems and so on. That's really helpful, this feature. And neighbor communication is now usable because all vendors have, or nearly all vendors have fixed their implementation bugs. And it's also usable because now the users can really read the standards, read the example, and use it instead of what is this doing? And it was one particularly in the MPI course who came to me, do I understand the standard wrong? Or is the implementation wrong? No, that was the basis of exactly that, and I went into the MPI form. Then these assertions are an additional feature for performance, and also this non-blocking send receives. And yet at the end we have an outlook to what's coming in the form and 5.0. Thank you very much. Do you have questions?
Thanks a lot, Rolf. Are there any questions? First of all, here in the room.
Okay, so I have 2 questions.
Yes.
First, more general question about the performance. I see in MPI 4.0, some new routine or semantic has been introduced, which purpose is to disable few features. For example, if I'm not using any MPI, any source, any tag, I can disable them.
Yeah.
So, and you provide the reason of introducing that semantic as a performance gain. So if we are not using it, we can disable. Just out of curiosity, is there any study in that direction which shows that how much performance gain I can expect with such kind of new semantics to be introduced in my program?
My expectation of these features is that they are first implemented in MPI libraries used on the top 10 systems in the world. Okay. This means it may be a feature that is used when they can for example, upload communication to the network interface controller. And if you don't have this network hardware on your system, then the MPI library will not do this, and you need not to care about, because this network interface controller can, for example, do only the matching for fixed tags and not for any tag.
Okay, so thank you for that. And the second question is more specific. So you have introduced one of the routines, which is like MPI request free.
Yes.
So I think I don't really get it, because in the non-blocking calls, we always have some routine for the testing, like MPI wait and MPI depth. And so this is done for after
No, MPI request free is MPI 1. Okay. And one nice way of misusing MPI request free is calling it for your send or receive request handle instead of calling MPI wait.
Okay.
And now we have wording that we tell that this is a misusing. Should never do this. And it should be used only and really only for inactive persistent request handles.
That makes sense. Thank you.
Okay.
Joachim from Aachen, for the assertions, you should not expect impact with low number of on-the-fly messages, but significant impact with large number of outstanding communications sitting in queues. So assertions have most impact when there's a large number of outstanding communications.
Yes. Okay.
I have a general question about new features like partitioned point-to-point communication. So who typically initiates that? Is it always the top 10 systems, people who think this could be a good idea for this particular application I am having, and then let's just push it into the standard? Or is it from vendors that can optimize things better? So what's the typical course of action for a new feature? Because some of these features for me seem a little bit academic.
Yeah, it's okay. I'm not 100% sure, because I've never looked on that. Is somebody coming from a vendor or from these large labs? But for me, it looks like that in principle, it's coming from the community of the people providing and using these top 10 systems. That's because there is this hard goal that they must be efficient. They must prove that $100 million system is efficiently used, and they have, for example, at Argon, when I understood correctly, they have each Monday the possibility that users can use the whole system. And for those applications, they still scale. This is a hard business, and they are typically inventor for non-features to have additional efficiency. Whereas somebody who uses in principle compute time in the scale only of 5,000 euro or dollar, I always say, oh, don't care about, never spend more than 1 month. This means never spend more than your salary in any optimizations. Because when you are doing some optimization, you get only 10% of that. You use 5,000 euro compute time, spend a maximum of 500 euro in optimizations, because when you spend more time, then you did wrong with your work and PhD. And other areas of people who care about performance may also come from large community codes, developing large community codes. Because then they know, okay, this is also an area of millions of euro or dollar of compute time. Does it answer a little bit your question?
Any more questions? It's still the same. Yeah. No, don't worry. I have a question about the sessions model. That's something that most of our viewers haven't come across. Can you say a couple of words about that? What does it mean, and what's the benefit?
The sessions model. The sessions model is each independent software layer can do first a session init. Based on the session init, it can do, this is a session handler, then it can produce a world group. It's really the keyword MPI world is standardized. And based on the world group, it can create an own world communication. And this all is then within such a software layer that you or some independent vendor provides. Like PETSI, for example. Solver library like PETSI. And then all communication can be done instead of a duplicate of MPI convert. All communication within PETSI can be done through this communicator based through this PETSI world communicator. That's one thing. Another thing that they think about is with the sessions model that that can also provide complete different groups. For example, only a group of processes having together third-level cache, for example. All these things. This means that the session model is also used for some optimized communications within a given hardware, for example, communicating within a GPU or whatever. These areas, this means that this part is also driven by groups having such a $100 million system with a very special hardware design inside. 3 GPUs plus 2 CPUs, or these things with a very special network combining them. And at the end, you must do a corresponding finalize. Is there a limit of sessions that can be handled? In principle, all MPI libraries have a limit on how many, what is the name for that? How many things like communicator file handles and so on can be produced. For example, 2,000 of them, but there's an environment variable. Before you start MPI run, you can change it and then you can produce 4,000 because they have a fixed array inside of these identifiers they are using. They are disjuncted of the whole MPI library.
There's a question online from Dimitri. Does one-sided communication need a complete rewrite?
There are ideas to produce a new RMA chapter in principle. I'm not sure what's coming out at the end of that. Will this, when they're doing a rewrite, will this end up in a way that the current use cases can still be implemented, that the old interface can be deprecated or not? I'm not sure. And one idea on the table is really to use, in principle, an MPI interface that fits exactly to the OpenSHMEM, which is formerly GreySHMEM, because that is a successful interface with lowest latencies and highest bandwidth. But one must see that typically these interfaces require that the application programmer must handle, for example, all the cache coherence things like the memory fences, and you will see what is really provided to the MPI form in the future. So that's a question for MPI 5 and not for 1.
Okay. So there's no more questions.
I think there was another raised hand.
It's gone again. Okay, so if there are no more questions,
Okay.
Rolf, thank you again for this talk. And everyone else, goodbye. See you next time. The next PerfLab seminar talk is on November 8th.